எல்லாருக்கும் கேக்குது நம்புறேன்.
Yes, sir.
Yes, okay, fine. Okay, good evening. So last classல வந்து we looked at laws of motion. So இன்னைக்கு வந்து I planned up with the next chapter. So we are moving on to a new chapter today.
I will tell you the background of this.
Fifth
I have
chapter
taken
போறோம்.
this picture in my house. This is my another house in Coimbatore. They were actually selling.
So we'll
I
start.
took them to my house and bought one mat.
I hope we can
That
start.
time I
It's
took
already
the picture.
time. So let me just start sharing my screen. என்னோட screen வந்து நான் share பண்றேன். Just let me know if you guys are able to
Those
see
things are
it.
not important, but I'm just saying that. Anyway, thank you, madam. I think it's almost 7:05. So thank you so much. Thank you so much.
Yes, உங்களால பார்க்க முடியுதா? I hope
So
everybody is
children,
able to see.
whatever we are doing, I'm going to send those PPT, etc. This video also will be there.
Yes, okay, fine. So today's chapter is quite simple. Work, energy and power. So அதுதான் the chapter that I have planned for today.
The video once or twice.
So இது வந்து நீங்க 8th 7th 8th 9th standardல இருந்து நீங்க படிச்சிட்டு இருப்பீங்க.
Okay, you listen to this
basic
video.
concept.
That would be better for you. Yeah. So here, because it is a madam, because it is a spoken language, they have to listen.
When is work set to be done?
That is very important.
Anybody?
So you have to listen to the video.
When can we say that we are doing work in physics?
Come to the next class. Before that, you will listen at least once. Okay? Okay, thank you.
Yes, any volunteers?
Dhanyavad.
When a mechanical state of the body is changed.
Okay, when the mechanical state of a body or a device?
A body?
A body, yeah, that's also correct. Yes. So when the state of the body is going to change, that is from, it can be from one place to another. That's also right. Yes. So that is, but a condition would definitely apply. So when you apply force,
Mani,
and
sorry
then
for interruption.
Yes.
I had another class till 7:05.
Okay.
That's the reason. I will introduce Manish because it is a new teacher for you. This is the first class for the 2025 Neet JE batch. That is 11th standard batch. And Manish has been, he's teaching the 12th standard students for the more than 1.5 years. He's one of the best teachers in IOM. So Manish, I request you to help our students, 11th standard students.
Sure,
the way you help the 12th standard students, similarly you help they're all brilliant students, and I think we should help them in achieving their objective, whatever be the objective. Students, Manish is considered to be one of the best teacher in online in India for physics, and he's a man who can teach physics, chemistry and mathematics.
Yes, uncle.
All three. I think
physics,
not mathematics,
and
biology. Sorry,
biology.
Bio, chemistry, and physics. He can teach equally well. நம்ப முடியுதாமா? Hello. என்னாலே நம்ப முடியல. Because for first 6 months he taught chemistry for us, and later on I have requested him to teach physics. Biology I have not tried, but he is too good because his mother also said he is too good in all the three. So that is the kind of caliber that we have. That is the kind of teacher we have. Make use of him, and he is considered to be one of the best teacher in the country for physics. So இது வந்து நான் அண்டர்லைன் பண்ணணும். Through online he is too good. நானே அந்த மாதிரி ஒரு டீச்சரை பார்த்ததில்ல என் வாழ்க்கையில். அந்த மாதிரி ஒரு டீச்சர். You make use of him. Go ahead, Manish. Sorry for the interruption.
Okay. No worries. It means a lot. Thank you, uncle. So welcome again, kids. So we have already started off with, so இன்னைக்கு வந்து நம்ம இந்த chapter வந்து will just have a brief intro. So and basic concepts also I'll be covering, and of course a few numericals also, competitive based numericals. That is what I've planned for the day. So work is what we were talking about. So coming back to our conversation, so one of you rightly said that the mechanical state of the body can definitely change. And I would just like to add a very small point to that. So when you apply force and the mechanical state of the body is going to change, be from one place to another, then you say that work is being done. Okay, so that's the basic idea of basically doing work. So I'll just put it here. So when do you say work is done? When you apply force on an object and the object is going to move or get displaced from one position to another, then you say work is done. So I'll try to represent that I'll try to represent it here. I'll try to illustrate it pictorially so that you have an idea. So I'm considering a block. You can see here I've drawn a horizontal plane and I've placed a block over the horizontal plane, and I'm trying to apply a force. Say the force is F. Okay, so I've represented that also. Now the block is initially, say, at point A, as you can see. Okay, and after I apply force, it's going to move from point A to another point, say B. Okay, so this is the displacement of the object from one point to another. So the object is moving from one place to another place, like this. Okay, so when you apply force and the object moves, then you do work. But when you apply force, and what if the object does not move? Say you're trying to push a truck, but obviously the force that we apply would be much lesser, so the truck wouldn't move. So can anybody tell me, is work done in pushing a truck if one person is going to push a truck and it does not move? Yeah.
Force, the force is applied, but there is no movement from one.
Yes. Yes, there is no movement. Then what happens? Then can we tell that work is done?
I don't think so.
No, yeah. So we don't do work because the object has to move. It has to get displaced from one position to another position. Only then, we can say work is done. Otherwise, work is not done. Obviously, even, we are applying force. All right. Yeah. So these are two important criterias that you have to keep in mind. First one is application of force, and second is the object has to move from one point to another or get displaced from one point to another. Okay, so that's the reason we express work as the dot product of force and displacement. So we can write it as vector force vector dot displacement vector. So this is a dot product. Now this is an application of vectors, which you guys would obviously have an idea about. So I'm going to expand the vector. Let me just give you an idea. Dot product of two vectors, vector A and vector B, can be expressed as AB cos theta. Okay, this is a formula of dot product. The same thing we would do here as well. So here it's F times S into cos theta, where theta is the angle between force and the displacement vector. Okay, so this is something that you will have to keep in mind. Now, in the situation given above, can you guys see that I'm applying force in the horizontal plane? The object is also getting displaced in the horizontal plane. Now, both vectors are aligned together or overlap together. In this case, what is the angle theta if both of them are overlapped? Both force and displacement vector?
One, sir.
No, it is zero, right? If it's
Yeah.
overlapping, yeah? So theta is 0 degrees in the case that we are discussing here. So if theta is 0, now I'm substituting cos theta wherein theta is 0. So I would just get F dot S, force into displacement. That's it. So that's the formula for work done. Okay. This is when theta is 0. Not necessarily all the time theta has to be 0. So conditions would apply. Okay. So the general formula is the one I've boxed above. And if theta is going to be 0 or the angle is 0, the second formula would apply. Okay. So this is the general formula.
Cos theta 0
Okay.
தானா செக் பண்ணிக்கங்க ஸ்டூடெண்ட்ஸ். இஸ் cos theta 0?
In the situation that I've given above,
Sorry,
you can
cos
see.
theta, sir, cos theta 1. Cos 0 is 1. Sorry, check. Cos 0 is 1.
Yeah, cos 0 is 1, isn't it?
Yeah. Sin 0.
That's the reason we get force times displacement.
இருங்க ஒரே நிமிஷம். sin 0 எவ்வளோ? sin 0 எவ்வளோ?
Zero, sir.
sin 0 0 வா?
Yes, that's
Yes.
correct.
0. Okay.
Yes, sir.
Okay. Right.
Okay.
Okay.
Yeah.
Carry on.
Yeah. So now what I will do is I'm going to change the situation this time. So again, I'm taking a horizontal plane, but this time we have a block. Okay, let me take a block. I'm not applying force in the horizontal plane. Now I'm going to apply force at an angle to the horizontal plane. Say this is my force vector. So I'm applying a force of say 15 newtons, but at an angle of inclination. Say the angle of inclination is 30 degrees in this case. Okay, it's 30 degrees, and the object is getting displaced. Say this is the initial point. So initial point, let me take it as A. It is moving to another point B along the horizontal plane. The distance between A and B is, say it is 5 meters. Okay. Now the question is, what is the work done in this case? For the case which is given above, what is work done? You will have to calculate work done for the given situation. The force is applied at an angle 30 degrees. So we try to find out what is the work done in this case. So anybody can try. Displacement is also given in the question as 5 meters. We have force as 50 newtons at an angle of 30 degrees.
I have seen only some powder fight in my life.
250
Yes. How would you substitute? Yeah.
force into S, F into S.
Okay. F into S. That's it. Well, you have to consider the theta also, right?
Cos theta.
Yes, sir.
Yeah, Fs cos theta. So you substitute here because we have an angle here. Previous case that was not, there was no angle, meaning it was 0. But this time we have an angle. So it is Fs 15 newtons. That's correct. 50 into displacement is 5 meters times cos 30 degrees. What is the value of cos 30?
Root 3.
3 by 2.
Correct. It's root 3 upon 2. Yeah. Now we can simplify it further. So you can write this as 25 times 5, which is?
125 root 3.
Yes. Answer is 125 root 3. Now what about the unit of work done? How can we express? Yeah, it is joules. Okay. So the answer is 125 root 3 joules. Now this is the magnitude. Okay, the positive sign represents the direction because it's towards the right. Okay, so work done is clearly a vector quantity. So as you can see here, we have calculated the work done for the given case where you apply a force of 50 newtons at an angle of 30 degrees. Okay, we can calculate the work done as shown. Okay, so why I'm showing you this is you should be aware of calculating or computing the work done at an angle when the angle is specified. Okay. So let's move on. So I hope the work done now concept is up. Okay. So same way the dimensional formula for work done. How to write the dimensional formula? Let's look at it. So how can we write the dimensional formula for work? Okay, so we know that the formula for work is force into displacement into cos theta, general formula. Okay, now if theta is going to be some angle, I would represent it becomes a number, right? So if I say 30 degrees, you said it is 3 by 2. If it is going to be 60, it is 1 by 2. So whatever may be the value. So ultimately it is force and displacement that decide the dimensional formula. So for force, I hope you guys know the formula for force, right? Which is mass into acceleration, and displacement we can just keep it as S itself. Now you will go ahead and write the individual dimensional formulas for mass. You know that mass is in kilograms. Acceleration has got the unit. Any guess? Any guesses? It is meters per second squared, right? And displacement has got the unit meters. Now we move ahead and we write the dimensional formula. So dimensional formula has got three major elements: mass, length, and time. So we need to appropriately specify the exponential values. Just have one mass term, that is kg. So mass would just be m to the power 1. L represents length. So here you can see there are two terms which represent length. Okay, so it is meter squared, so we can write this as L square. But there is a time term that is second squared in the denominator. So you bring it to the numerator, the sign would change, so it becomes -2. Okay, so the dimensional formula is m L squared t power -2. So this is how you calculate. Okay, this is how you write the dimensional formula for any physical quantity. Okay, I hope this is clear how to evaluate the dimensional formula for work. Okay, so this is how you do it. All right, so now we'll move on. So this is, a concept that is necessary. So we'll see the next concept. So we are done with work done. Now we look at work done by a variable force. Okay, so now the forces that we applied was, a constant force. Now what if the force is going to be a variable force? Okay, so work done by a variable force. So we look at that. Okay, so I'll give you the expression. So work done by a variable force is given by integral f of x into dx. Okay, so here we represent using an integration, okay, of force. So we try to sum up all the strips. You try to get the entire work done for a given a specific interval. Okay, so it can be from initial position xi to final position xf. So we can represent this using a graph. So I'll represent it using a graph where we have a displacement versus force graph. Okay, so y-axis I'm representing force as a function of displacement, and in the x-axis we have the positions, initial position and the final position. Okay, wherein the force can be a variable force. So this region, you can see, is given by the work done in this region. That is when force is applied from initial position xi to a final position xf. So by integrating, we can find out the work done for the entire, position, the entire, length, or the entire displacement when the force was being applied, when the variable force was applied. So this is how we represent it graphically. And this is the formula that is in front of you. Sequence basis. Let me just so for you to just try. Okay. Calculate. Give it the work by the variable force value by the function. I'm giving you the function. Okay, so f of x is equal. Simple question: x square plus 5x plus 8. Okay, I'm giving you a function assignment. Calculate the work done by a variable force represented by the function 2x square plus 5x minus 8. Okay, between or the interval also for the displacement interval, or let me put it from 2 less than x less than 4. Okay, 2 meters less than or equal to x less than or equal to 4. So I'm giving you a range. So for this range, you will have to calculate what is the work done. Okay, that is the question. So when you have a question like this, now let the given data. We have two, sets of data. So we have to calculate what is the work done. So this is a variable force because you can see the force is represented using a function. Okay, it is modeled using a function, which is having a variable in it, right? You have an x variable in it. So we will have to find out what is the work done for this variable force. So you make use of the formula above. So the general formula is work done is represented using the integral of force as a function of displacement or position times dx. This is the general formula. Now, what are the limits that we have to apply? You can see here we have the limits specified in the given range, right? It's from 2 to 4. So I'm specifying it from 2 to 4. Okay. So now, even before we proceed, with solving the question, you guys have an idea about the formula for integration, the basic formula, integration of x or n. I hope you guys know it.
X power n plus 1 divided by n plus 1.
Yes, it's x power n plus 1 upon n plus 1. This is the formula. Okay. So now let me go and substitute the value of force. So we have limits from 2 to 4. Force is 2x square plus 5x minus 8. So let me go and substitute the values. Let me try to integrate. So here we have the first term as 2x square. Okay. So constants can be removed out of the integral sign. So 2 is a constant, take it out. 2 times integration 2 to 4 x square into dx. Okay. And you again have 5 as a constant. I'm removing out of the integral sign. So integral x into dx. Again limits from 2 to 4. Minus. Now constant terms can be or is it 0? Can we integrate a constant term?
Can be integrated, sir.
Yes, you can, right? Only for differentiation it's 0, right? But for integration you can integrate. So minus 8 times, if nothing is there, you just write it as 1 into dx. Okay, 8 times 1 is 8, of course. Okay, so it's 1 times dx. So again, limits from 2 to 4. So this is what we do. Okay, now let's try to integrate. So 2 times, what is integration of x square? Go with the formula. So you would get integration of x square as x power n plus 1. So 2 plus 1 becomes 3. So x cube by 3. I hope that's clear. X power n plus 1 upon n plus 1. For x square, n was 2. That's the reason 2 plus 1 gives 3 upon 3. Okay. So limits from 2 to 4. The same way you would proceed for the other terms. Plus 5 times. What is the integration of x? Anybody? Here n is 1.
X square by 2, sir.
Yes, it is x square upon 2. Limits from 2 to 4. Minus 8. Integration of dx would give you
X.
x. That's right. X limits again 2 to 4. Now you go with solving this. Okay, so again we can write this as 2 upon 3 because 3 is a constant. I'm taking it out. So we need to resolve the limits here. So upper limit minus lower limit. You can see the upper limit is 4 and the lower limit is 2. Okay, for each of the terms. So you can just need to substitute the limit value. Okay, x cube is of course there. That's the variable. So you substitute the value 4 for x in the first term, which gives you 4 cube minus 2 cube. Okay, so you proceed like this. Plus 5 upon 2 times, again in the place of x square, for x I substitute the upper limit as 4. So it gives you 4 squared minus 2 squared. The same way you proceed. Here it just gives you minus 2 because it's just x. Okay, so you need to now proceed and simplify this. So what is 4 cube minus 2 cube? You can apply a cube minus b cube also and solve, or directly you can simplify it. Yeah, so what is the value of 4 cube?
64
Yeah, so 64. So we get 64
minus 8.
minus 8. That's correct. Same way, 5 upon 2 times 4 square is 16 minus 4, and this is 8 times 2. That's it, right? So simplify it. 64 minus 8 upon times 2 by 3. What is the value that you guys are getting?
56.
56 you're getting? Okay. Again, 56 times 2 upon 3. I think you're getting 112 by 3. Just check because I'm doing an oral calculation. Yeah. And 5 by 2, 16 minus 4. You multiply with 5 by 2 and tell me how much you're getting
30, sir.
so that we can verify.
30, sir.
30. Okay. That's correct. Minus 16. Yes. So you simplify this, children.
51.33 joules, sir.
You're getting 154 upon 3 when you do the LCM and simplify, isn't it?
Yes,
You will
sir.
get 154 upon 3, and in decimals you will get the answer as 51. Yeah,
51.33.
0.3. I think it's recurring, so I'll put a dash. So 51.3 recurring. Okay, so now this is the work done. So the unit is going to be joules. Okay, so the answer is, okay, work done is equal to 51.3 recurring joules. That's it. So this is the answer. Okay, I
Sir,
hope it's, yeah.
can you please scroll down to the starting of the sum,
Sure,
sir?
sure.
Thank you, sir.
Yeah. So step by step approach. I went slow because it's the first class, and obviously you guys should catch up to my speed. So I hope I'm not going too fast, right? In case you can let me know, I lower my pace. Okay. I hope it's understandable to all of you.
Yes, sir.
Okay,
Yes,
great.
sir.
Okay. Fine. So this is how you do it, children. So this is a calculus approach. Questions based on the difficulty level. You can have questions coming up from calculus approach also. That's the reason I discussed this question. Now let's move on to the next concept. We are done with both work done. The work done involving angle is done, and the work done involving a variable force, that also we have now learned. Now we are moving on to the next concept of work done, third concept, which is work done by a spring. Okay, that's what we are going to look at. Just write it here. So now we are going to see what is the work done by a spring. Okay, so now trying to show you, explain the concept of work done by a spring. So let's take a simple spring attached to a rigid support, as you can see. Okay, and we have a spring like this. So there is a spring, and then you're trying to apply a force towards the spring. So force can be applied, and you're trying to extend a spring, or even you can try to compress a spring. There are two different ways of looking at this concept. So here I am applying a force, and I'm trying to extend the spring. Okay, so the initial length of the spring, as you can see, is, say this, the initial length of the spring is x. Okay, this is the initial. Now, after I've applied a force, the spring is obviously going to extend, or it is going to expand. Okay, so this case is before expansion. Now I'm going to draw it below and show you after expansion how it is going to look like. Okay, so once you expand, the spring gets dilated. Okay, and it will increase in length. Once you expand like this, and so it gets expanded after you applied a force. The first one is before application of force. So okay, let me just remove that f, might be confusing. So now I'm applying a force. Now after applying force, you can see the spring is now expanded. Okay, I mean it is extended. Okay, so again we try to understand by how much it is extended. So you can see here this much it is extended. So let me call this as x dash. Okay, so that is the extension. I have shown you the extension directly. Okay, so there is one more way of looking at this. Instead of showing just the extension part, what I will do from the basic point, from the starting point itself, if I'm going to measure end-to-end length from of the spring, we can represent this as, say, final length. Let initial length be x1, let x2 be the final length. Okay, after I've applied a force, then what would be the extension of the spring or elongation of the spring? How can
Q
we
minus
calculate?
Q.
Yeah, so extension or elongation in this case is given by delta x, which is x2 minus x1. Okay, so that gives you the extension by how much it is extended. That's a simple idea. Okay, so now we try to find out what is the work done in applying a force on a spring and you trying to extend it. Okay, so that's given by the relation work done W is equal to, here also we try to go for an integration. So we can apply the same formula that we learned above. So say integration of of x into dx. Now the force that I'm applying is basically the force which is necessary to expand this string, okay, or the spring here in this case. So it is given by Hooke's law. Now Hooke's law is again something that you guys would have come across. So integration of, in the place of f of x, in one I'm going to substitute
K,
slow
K,
relationship,
K,
yes, which is, yeah, kx. But why do I put a minus sign here? We can say kx, but why minus
sir,
kx?
because opposites to force, sir.
Yes. Now, when you apply a force on the spring is also going to exert an equal and opposite force in the reverse direction, which is given by Newton's third law. Every action has equal and opposite reaction, right? We have learned that. That's the reason we put a minus sign. So minus kx times your expansion, so dx. Now, what we do, I told you, whenever you go for an integration, you can remove the constant term out. So here the constant is k, isn't it? So I can minus k outside integration of x into dx. Simple. So you into d. What happens? What do you get in the process?
Minus K x square. X square
Yeah.
by 2.
Yes. Minus k times x squared by 2. And this is what we get, children. So this is the work done by a spring minus k x square upon 2. Okay. So this is the relation. So this is how we got the relation. Okay. How you're explaining. Now here we've done for, I've given you the example of elongation. Work is being, it can be done by also be okay. So now this is a spring. That is compression elongation formula works good. Is also the final, right? Moving about done possible. In this form the work by a spring, you can also come possible for compression. So with that, we move ahead. Then we have the concept of energy. So we are done with work. Now we are moving on to the next concept of energy. So what is energy? The basic idea of energy. Any idea?
Something that we require to do work, sir.
Yes, that's correct. So energy is something that you require to do work. So we can say that enables a body to do work, right? Energy is something which enables the body to perform work or to do work. Okay. Unlike work done, energy is also having the same unit, joules. Okay. That's correct. So energy in simple terms, we can say the rate. Um, okay, instead of saying the rate, let me put it this way. It enables a body to do work. Okay, simple. So that's a basic idea of energy. So energy, we have two prominent types of energy. Okay, we can bifurcate energy into two types, basic two types. You have many types. Okay, so we'll look at two basic types of energy. One is kinetic energy. and the second one is potential energy. Okay, so two prominent types that are necessary for us. So, what do you mean by kinetic energy? So, when do you say an object is possessing kinetic energy? Under what circumstances?
Energy required in motion is called kinetic energy.
Yes, the energy possessed by an object when it is moving or when the object is in motion. Absolutely right. Then you say kinetic energy. So, real life examples. So, you can say moving vehicles if you're going to walk, or an athlete who's running. Okay, you can give many examples. Birds, flying birds, right? An athlete run. Objects which are stationary, which are at rest. Would they have kinetic energy?
No, sir.
No.
No. No, right? Zero, because the velocity is zero. Their initial velocity is zero. So they don't have kinetic energy. Okay. So the basic formula for kinetic energy is half mv squared. So this is the formula for kinetic energy, where m is mass in kilograms and v is velocity in meters per second. Okay. Is meters per second. Okay. Yeah. So this is the formula for kinetic energy. As I said, the unit is joules. Okay. And same way we have potential energy. So an object can have potential energy, based on subjective conditions. I hope you guys know what is potential energy. It's just a basic idea. Just give you the formula. You can tell me what is potential energy also. Yeah. Any idea for potential energy? And
They found in a body, sir.
the energy found in a body. Okay. Almost.
Energy required at rest.
Okay. Fine. See, potential energy is basically, the energy that a body would possess due to the position of the an object. Okay, due to its position. That's it. So we don't talk about whether it is moving or not. All right, due to its position, it can be at any particular position from the ground level. Okay, so here you can see there is a term called height. So as height increases or altitude increases, what happens to potential energy? That also would increase, right? Because it's directly proportional. Fine. Energy is something varies with respect to height or altitude. So these are two basic ideas that you're showing. Variation. All right.
Directly proportional, sir.
Yes, it's directly proportional to the height of an object. Okay. So that's something that the height you'll have to know for potential energy. All right. So now let's see next concept of momentum. Okay. So momentum is given by the letter P. So what is momentum?
Mass into velocity.
Yeah. Yeah. So momentum is basically what you said is the formula, but I was asking for the definition. It's okay. So momentum is basically the
Effect
combined.
of
Huh?
the effect of force.
Yes. You can say it's the effect of force. Momentum is basically the combined effect of an object with a particular mass along with its velocity. Okay. So that is momentum. The combined effect of an object with mass m moving with a certain velocity, you say that it is having some momentum. Okay, so as you rightly said, it is a product of mass and velocity. So you know that the unit of mass is kilograms and the unit of velocity is meters per second. So what would be the unit of momentum? It is kilogram meters per second. All right, so that is the combined unit of momentum. All right. So this is a basic idea. Now, how do we connect kinetic energy and momentum? What is the relation between kinetic energy and momentum. How can we relate both of these terms? You know that kinetic energy is
1 by 2 mv square.
half mv square. So how can we bring in momentum term here? Can we write kinetic energy as G? Now I'm trying for rearrangement, okay, purely in terms of momentum. Okay, I don't want velocity term there. Okay, so in the place of velocity, if I'm going to go for a rearrangement, what do I get? I can write it as half m. In the place of v, I can substitute p upon m. Is that right? Can I do that? Yeah.
Yes, sir.
So what would I get in that case? Half m times p squared upon m squared. So one m would get cancelled, and finally I'm left with p square upon 2m. So this is the relation between kinetic energy and momentum. So we can say momentum is equal to under root twice the mass into kinetic energy. Okay, so this is another relation when I go for a rearrangement. All right. So these are two prominent relations for kinetic energy and momentum. So this is something that is very useful for us. Okay, this result is very useful for solving certain questions. Okay, so that's the reason I explained this part. So now we are moving on. Okay, so we are done with energy, the basic aspects of energy, kinetic energy, potential energy, and we also looked at what is momentum and related both momentum and kinetic energy. So that's what we have done so far. Okay, so with that, proceeding further, I hope it's clear so far. We'll go into the next concept of work energy theorem. Okay, this theorem is very important that and it gives you the information between the relation between work and energy. Okay, it's very simple. What this theorem states, it states that the work done, okay, work done, or you can say total work done on an object is equal to change in its kinetic energy. Okay, so basically change in energy. Okay, so when you try to do work on an object, then it's equal to change in its kinetic energy, because you say that when work is done, the object is moving right from one place to another. Obviously it's going to have some velocity, so and it's changing its position also. Therefore you can say that work done is related to change in kinetic energy. So this theorem can be expressed mathematically as work is equal to delta ke. Now what this delta sign or the triangle sign represent? It represents change. Okay, the triangle sign represents change or change in. Okay, so if I say delta ke, it is change in kinetic energy. So how can I express that? It's delta half mv squared. Now here mass is constant, you can take it out. Half is also constant, you can write half m times delta v squared. Okay, that's velocity squared. So when an object is being pushed with a force, obviously the velocity would change, right? So it is initial velocity squared minus final velocity squared, which is, okay, change in velocity is final minus initial. Okay, let me put it that way. So v squared minus u squared. So this is what I would get when I go to substitute. Okay, simple. So which is same as final kinetic energy minus initial kinetic energy. Okay, so this is how we can express it mathematically. When you go to express, so we can express change in kinetic energy as final kinetic energy minus initial kinetic energy. You can just check if you're getting the same term. Formula for final kinetic energy is half m. We use the final velocity term. Same way for initial kinetic energy, I would use u instead of v, right? And if you take a common out, obviously you would get back the same expression, right? I hope it makes sense. So this is how you try to relate work done and change in kinetic energy. So work done is equal to change in kinetic energy as expressed here. Okay, I hope this part is clear. Yeah. So this
Yes,
is
sir.
work energy theorem. Simple. Okay. So now we are done with work done, and we have also done with the work energy theorem, how it relates, both these concepts. So now we are moving on eventually, with respect to the gravitational, energies. So gravitational potential energy is something that we are looking at now again. This also, you guys would have come across, but still I would be explaining it here. So I'll give you the basic formulas. I wanted to cover a couple of questions also today. I've planned, a few questions. Yeah, I'll give you the formulas now. First one is the gravitational potential energy. Now, what is gravitational potential energy is basically when you have two objects, with masses m1 and m2, okay, and when they are separated in space by some distance, let me say I'm having two objects m1, say another object m2, okay, obviously m1 is not equal to m2. That is the condition. And the distance of separation from their centers, let me say this distance is r, okay, the distance between them is r. Then the gravitational potential energy is given by u is equal to negative g m1 m2 upon r square. Okay, so this is the formula. This comes from Newton's law of gravitation. It's an application of Newton's law of gravitation. So you can see capital G is the universal gravitational constant. Okay, so the value of G is 6.67 times 10 raised to negative 11. Okay, Newton meter square upon kilogram square. And this is the unit along with its magnitude. Okay, you need not remember all this. This would basically be printed, and this value is already given. This would be available in the data sheet, so you will obviously get this. So this is a constant, okay, which is your universal gravitational constant. All right. Yeah. And if an object is at certain height, say from any particular planet or from the surface of the earth, say, so in that case this formula gets modified as u is equal to mgh. So it's the potential energy per unit height. So for the height from the surface of the earth is written as 1 plus h upon r, where r is the radius of the earth, h is the height from the surface of the earth, and m is the mass of the object. Okay, this is the gravitational potential energy associated with an object at a certain height. Okay, so let me write it there. So this is gravitational potential energy at a height h. Okay, for that we make use of this formula. M is mass, g is acceleration due to gravity. I hope you guys would be knowing. Its value is 9.8 meters per second square. All right, so that's a constant. So these formulas are again, very important for us to solve certain questions. Based on the given data, we use this formula. Okay, so that's about this. Okay, so that is all about the gravitational potential energy. And then we have the law of conservation of momentum. Okay, very important. So Can anybody tell me what is the law of conservation of momentum? When do you say momentum is conserved? Yeah, it tells you that.
The total momentum in isolated system is always conserved.
Yes, so that means the total momentum before impact
Is equal to total momentum of after impact.
yes is equal to total momentum after impact. Okay, simple as this. This is basically the statement of law of conservation of momentum. I've put it in a simple way. Total momentum before impact is equal to total momentum after impact. Now, what do we understand by the term impact? Impact means to collide with. Okay, so
Collusion.
yeah, it's collision. Collision. We come across collisions, in our day-to-day life. Collisions can be elastic or non-elastic. We'll come to that next. But collision, as in, it's when two objects have a head-on-head impact with each other. We say that they collide with each other, or in simple terms or local terms, we say they dash over each other, right? So that is, basically the meaning for impact or to collide. Okay. So the total momentum before collision is equal to the total momentum after collision. So to prove this statement, first we can take an example. Okay, let us assume two objects. Say I'm taking one object of mass m1. It is moving with initial velocity u1. All right. At the same time, there is another object with mass m2 moving with initial velocity u2 ahead of mass m1, that is before mass m1 or in front of mass m1. So there's the first object a, this is the second object b. Okay, so I'm representing this diagrammatically. This situation is before impact. Okay, before impact. Now, what if u1 is greater than u2? If the velocity of the first object is greater than the second, now can you tell me which object would go and collide with which object? They're moving along the same straight path, one behind the other. So would object A collide with B or B collide with A? Which is
A
possible?
would collide with B, sir.
Yes, that's correct. So A is going to collide with B because A is moving with a velocity greater than B along the same straight line. And therefore, during impact, how would the situation look like? It's going to look like this when both of them are going to collide. That is, A is going to collide with B. Now you can see that this is how it's going to look. Okay, this is during impact or during. All right. Now, collision, there's one important aspect that we need to understand. When two objects collide or one object is going to collide with the other, during aspect that the impact is going to be observed by both of them, or it is felt by both objects. It's not just the object which is going to go and collide. Not necessarily. All right. Now you have both object A and object B that are colliding. So, according to Newton's third law of motion, you know that every action has got equal and opposite reaction. So when A goes and collides with B, obviously B is also going to have an effect on A, right, in the reverse direction. So collides with B, A is going to apply a force with that B in the direction as FAB. Similarly, object B is also going to exert force on A itself in the reverse as per Newton's third law, which is FBA. Are you guys getting the point? So then to experience forces in opposite directions. This is Newton's Newton's law of motions in the Newton's third. Okay, this is how both of this purely. All right. Now, having understood this, we try to express this mathematically. Okay, so FAB is towards the right is equal to, it's both of them are equal and opposite, and hence I use a negative sign convention. FAB equals minus FBA. Why am I putting a negative sign for FBA? You can see the force is towards the left, negative direction, and hence the negative sign. Okay, I hope this is clear. Right? Any doubts in this concept? I hope it's clear.
Yes, sir.
This part during collision or during impact. All of you, are you here?
Sir.
Yes. How the forces are acting, how they're interacting in the reverse directions, how forces exerted by A over B towards the right, and same way, B towards A or towards left. Okay, this is from Newton's third law. Now let me substitute the formula for force. Who can tell me the formula for force from Newton's third law? F is equal to,
MES.
yes,
Mass into acceleration.
I think you guys told me a few minutes.
Mass into
So
acceleration.
mass into acceleration, isn't it? Force equals mass into acceleration. So I go and substitute that for both the terms, the left hand term and the right hand term. So let me substitute. So force for both the terms, I'm substituting the formula. So I will get mass into acceleration for both the terms. So mass of object A, which is m1, times acceleration of the object A is a1, is equal to minus m2 times a2. So substitute the formula for acceleration. You know that acceleration is change in velocity upon time, right? So it's v1 minus u1 upon t. And for the second term, it's m2 times acceleration is for the second object. Object B is v2 minus u2 upon t. Now both the sides you can see time is common, can be cancelled off, right? So what do you get? So what do you get now? You get m1 times v1. Just you need to multiply. M1 times u1 is equal to negative m2 times v2 positive m2 u2. Okay. Go for a rearrangement. You can see that m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. Right. So can you see this is the derivation of law of conservation of momentum. The term on the left is the total momentum before impact. Okay, it's the total momentum before collision. And the term on the right is the momentum after collision. So we proved the law of conservation of momentum. Okay, very simple. So these are all the formulas in the chapter. So we have looked at all important formulas, and now we are moving on to the questions. Let's move on to the questions. So let me load questions. I'll again share a different screen. So we are going on to the question screen. I've started sharing the question screen. So let me know if you guys are able to see it. Is it visible? The question screen? I hope it's loaded and you're able to see it. Okay, so here is the first question. So I want you guys to go through the question and tell me how you will approach in solving this question. Okay. Yeah. So let's try to understand this even before we attempt solving it. Okay. So here's the question. A 5 kg block is kept on a platform at rest. Okay. And at time t equal to 0, the platform starts moving with a constant acceleration of 1 meters per second square. So the platform is moving, and they've given you the coefficient of friction mu between the block and the platform is 0.2. So there is a friction also which is present. The question is the work done by the force of friction on the block in the reference frame in 10 seconds. Now what is the force that is experienced by the block on the platform in a time duration of 10 seconds? That's the question. So you will have to first illustrate this question. You will have to try to illustrate it. I mean, draw the situation. Okay, and then you go for solving. Right? So let me try to draw it here on the right side. So here you have a platform. Here you have basically a horizontal plane. Then let me draw a platform. This is not the platform. Okay, this is a surface, a horizontal surface. Now let me show the platform here. Now this is a platform. Okay, we just write platform there. So this is the platform. On top platform, we have a block. Okay, so this kg block that I have shaded, you can see. That's a 5 kg block that is placed. All right, that's it. So this is what we have. This is the given situation. Now, once you have drawn the given situation, you will try to show all the forces that are acting. Okay. Now they're telling you that platform is moving, isn't it? So the platform starts moving with a constant acceleration. So the acceleration of the platform is going to be towards the right, isn't it? So acceleration is 1 meters per second square. That is given in the question. Now when platform starts moving, now you know that friction is also going to act, right? With respect to the object that is placed. It will act in the reverse direction. So force of friction is going to act in the reverse direction. So let me say small f. Okay. Apart from this, any other forces which are acting, can anybody identify? Are there only two forces? Force of applied force due to the acceleration and frictional force. Is there any other force that is going to act?
Normal force.
When block is placed, don't you think weight of the block is also going to act downwards? Isn't it? Vertically downwards. So weight will act, which is mg, mass into times gravity. And you also have a normal reaction that is going to act upwards. Now these are all the forces that are going to act. And whenever you have an object, you represent all the forces that are going to act on the object. Okay, so forces. So when you have an object with some mass kept on a horizontal plane, you have weight that acts downwards, obviously, because Earth is going to pull it with gravity. So G is acceleration due to gravity of the Earth, wherein M mass of the object. Say opposite force is a norm to Newton's third law. Okay, that is going to act vertically upwards, as always perpendicular surface in contact. Okay, so that's something that you will remember. Once I have drawn all the forces with respect to that's reaction, anyway, equal and option to the block. Apply. We have two. Let me do forces again here, and then we try upward normal try to solution. So I will vertically. Now we would go to solve the question. These are all forces that make normal force. Towards this is weight. Towards the side force to G is applied force. Towards the and this is force towards the left. Weight, which is MA. Okay. So once you have written all this and you have shown all the forces that are acting, now here you can see that the platform is moving with a concentration of 1 meters per second. That's what they've given us, right? Constant acceleration. So what is that? What is one by friction on the block? Okay. So our assumption and will be that the block friction will remain at rest to the platform is at rest, but platform is in motion. That's what is the idea. Okay. With that, we need to respect to the platform. So we know that it is that force from the is equal to mass into acceleration. Let's proceed and try to find out what is the force that is going to act. Now, what force is this here? That is a frictional force with respect to the block. Okay. So force of friction. Okay. So the force of friction. So how do we calculate the force of friction? I hope you guys have an idea of how to do it. Okay, so I'll anyways show you because we are doing it for the first time. Do that for now. Like apply formulas and let's do get the relationship. Okay, so I'm applying the formula mass into acceleration. Mass is given as 5 kg. So 5 kg into acceleration was 1 meters per second square. So 5 times 1 is just 5 newtons. So this is the force that is required to just make it move. Okay, so we had an idea. Now we are proceeding and we try to find out what is the force is newtons. 5 newtons is basic force. Okay, what is your normal reaction force in the vertical plane? You can see normal reaction is acting upwards. Weight is balancing the normal reaction as you can. So normal reaction corresponding is equal to the weight mg. Now, how much is that equal to? 5 times g is, we can assume it as 10. Okay, it becomes 50 newtons. Okay, so that is the normal reaction. And now we can proceed and we can see that your normal reaction is 50. And frictional force can also be calculated from using this formula. F is equal to mu into n. One is the force which is required to move the block. One more is purely the frictional force. So where mu is coefficient of friction, the value is given in the question as 0.2. Let me substitute that 0.2 times normal reaction, which we got that as 50. So multiply it. So how much is that? I think directly you can write 50 times 0.2, 2 upon 10, and you would get 10, right? So 10, you would get 10 if you solve it. So that's, the force of friction that is going to act. And you can see that the applied force is less. Okay, and hence the box is going off to remain at rest. Okay, it's just 10 newtons. It is going to act on the left side. Frictional force is 10 newtons. Okay, but applied force is just 5 newtons, and obviously the block cannot move as per the given conditions. Okay, so with that, you go displacement. Now, how can we find out the corresponding displacement of the object? Or how can we find out what is the work done? So for that, displacement is the ground. Because okay, you can see here now they have given you the time relationship, specific time relation to us here in the, so the displacement, I'm writing it here. Means we need the question because work done is force into displacement. So we have related to the ground. Okay, so that can be found out using the formula. Yes, who can tell me what is the relation we can use to find out displacement? Can we make use of equations of motions? We have learned, you have already learned 3 equations of motion. Right? S is equal to ut plus half at squared. Yes, so we can make use of that relation. So ut, u is 0, right? So half at square, a is 1, t square, t is given in the question as 10, so 10 square. So you simplify this, you would get 50 meters. Okay, displacement is 50. So once you have found the displacement, now you can find out what is the work done. Work done is again force into displacement. So force value, we try to substitute the value of force 5 into displacement as 50. So 5 times 50 is 250. Okay, so the answer you get it as 250. Not space is quite small. So 250 newtons, it is joules, right? Because it is the unit of work. That's it. So that's how you do it. You solve this question. So the answer is 250 joules. Okay. So based on the question, You need to identify the given situation and then you will have to find out. So this is the approach to solve this question. So now we'll move on to the next one. Okay, so this is another question. Now these questions are of, the difficulty levels are from moderate to, difficult. So first, based on the question, try to understand the given data, and then you will identify which formula is a perfect fit for us to solve the question. All right. So here comes another question. So go through this. So let's try to understand this first. An ideal mass spring can be compressed 1 meter by a force of 100 newtons. Okay, all spring is placed at the bottom of a friction of an inclined plane. You can see there is an inclined plane. It's inclined at 30 degrees, and the block has a mass of 10 kilograms. Okay, and it is released from rest. You can see it is on the top. When you release it from rest, it's going to go and hit the spring. Okay, and it is brought to rest momentarily after compressing the spring by 2 meters. That also they have given you. What is the speed of just before it reaches the spring? So when I read the question, so I will underline all the given data in this question. All the given data. Okay. So neatly we understand what is given. See, force is given here in this question. Data. So I'm going to specify give the force is 100 newtons. Done. This is one data. The second data is angle of inclination theta, just 30 degrees. Then you also have mass of the block, which is 10 kgs. And then you also have the displacement as 2 meters. Okay, and acceleration due to gravity, anyways, that is given in the question, 10 meters per second squared. So this is all the given data. So once you write the given data, you identify which approach would be the best approach. Now, because we have a spring, obviously you know that if it is going to be a spring, the formula related to a spring is what needs to be used, isn't it? So definitely we would use relations with respect to spring. So who can tell me what is the force involved for compressing or for elongating a spring? Right? Here force is applied on the spring. Spring is not applying force. So obviously it's going to be positive, right? So F is equal to K into X. That's a relation where K is your spring constant. Okay. Fine. So that's what they're telling. So they're telling it is compressed by 1 meter. That's also something which is given. Okay, the length they are telling of compression. So what is a spring constant? Don't you think it is going to be F upon X? Isn't it? Which is 100 upon 1 meter, because it is compressed by 1 meter, isn't it? By a force of 100 newtons. So your spring constant K is 100 upon 1, which is 100. So 100 newtons per meter. That is the value of spring constant. So that's the first thing that you'll have to do. Okay. So once you understand that, so now what happens when the mass is going to slide by a distance? Now we don't know what is the distance. So let us assume that it is going to slide some distance. Say it is sliding a distance of S meters. Okay, when it is released from rest. Okay. So how much does a spring gets compressed when it has been released? It is getting compressed by 2 meters. Okay. So it is already traveling S meters, and plus the spring is also getting compressed by 2 meters. So total distance that block is going to travel would be S plus 2. Okay. We darken it. So S plus 2 is the total distance traveled by the block of mass M. Okay, so this is the basic idea, and that is also present at an angle. This S plus 2 is your displacement vector. It is present at an angle of 30 degrees. Okay, to your inclined plane. So therefore its component, when you try to find out its component, obviously you know that the angle that is going to be involved here. Okay, you apply the corresponding angle and you can find out in the horizontal plane. Okay, now the mass is also given to us. So now let me try to write down the relationship. Okay, now the block is moving from a certain height. It is moving to another height. So obviously potential energy of this block needs to be considered. So what is the potential energy of the block? Potential energy of the system. Formula for potential energy, it's mgh. I'm trying to write capital M because mass is given as capital M. Okay, so mass times acceleration due to gravity, and the height is nothing but the displacement by which it is moving. Okay, it is moving by total distance of s plus 2. Okay, so but s plus upon 2. Anybody can tell me why I'm putting upon 2? Because I'm trying to find out its component, its vertical component, right? So what is a vertical component? If this is 30 degrees, this is going to be 90 minus theta, right? If you're trying to find out the vertical component, so that will be sine theta. Okay, so which is your 90 minus theta is going to be 60 degrees. You know that sine 60, sorry, sine 30, right? It's the component that is on the top here. So cos of 90 minus theta is sine theta, right? So that is what is the meaning. So it is sine 30 degrees. Okay, so when I do it, I'll do it like this: cos of 90 minus theta. That is what will fetch me the sine component, which is sine 30, not 60. Okay, it is 30. So once you do this, you can easily get the relation s plus 2 upon 2. Okay, so mgh is equal to mg. In the place of h, I am substituting your s plus 2 into sine 30 degrees because it's the vertical component. So that is what is giving me s plus 2 upon 2. That's the meaning. So once you have got that relationship, you know that there is a change in, as per work energy theorem, you can change in energy, right? So kinetic energy, obviously. So we can equate this to change in kinetic energy. So this term would be equal to half kx squared because the work is done by the spring. It collides with the spring. So it's the energy work involved in the spring. So it's half kx squared. We have already learned that. Okay. So go to equate it. So if half kx squared is equal to E into s plus 2 upon 2, then what is s? Just you simplify this. You know that k is 100. Okay, and substitute the value of x also as 2 meters, and g you can take it as 10. Mass, you can, is also given 10 kgs. Okay, substitute all the values, go for a simplification, you will get the answer value of s, okay, as 2 meters. Okay, you simplify this, you will get s as 2. Once you've got s as 2, you can now easily find out what is the speed or what is the velocity with which the object is going to move. Okay, so how can we find out that? The gain in kinetic energy should be equal to the loss in potential energy by the law of conservation of energy. Okay, that's what we do. So substitute kinetic energy, you know the formula is half mv squared is equal to loss in potential energy is mgh. You can see mm can get cancelled off. Okay, and then go for a rearrangement. You get v is equal to under root 2gh. Okay, which is under root 2 times g is 10 and h is nothing but the value of s that you have calculated. Okay, and so I'm going to go and substitute that value. So how much is that? So you go to substitute. So it's s upon 2, isn't it? Because the mass is falling out by a height. So obviously the component is s sine theta. I told you that's the reason I'm putting s upon. Okay, so 2 gets cancelled off and you get root 20 as the answer. 2. So root 20 meters per second. Okay, so this is how we solve this type of question. So this question is it requires the concepts of work energy theorem, resolution of vectors, which already you guys would have learned. Okay, so that is the basic prerequisite knowledge that is necessary to solve this question. So it's an application of work energy theorem, application of vectors, resolution of vectors, and law of conservation of energy, as well as Hooke's law. So there are four concepts which are involved in solving this question. So when you look at the step-by-step approach, this is how it needs to be done. Okay.
We close at this, Manish.
That's the reason I've taken this question. It's quite hard, I do understand that, but once you try solving it on your own, you will have a confidence. You can get a confidence. You can try to solve this question again on your own. I would suggest all of you to do that. Okay, try to solve the question again. Anyways, I have solved it here, but once you try to do it without looking at the solution, so that will boost your confidence level.
You will be sending this transcript, Manish.
Solve this question. So we have many questions like these. Some challenging questions are also there.
Manish, you will be sending this transcript?
So I think we'll wind up here. We are almost done.
Yeah.
Okay.
Correct.
So, yeah.
You will be sending
Any
this
doubts
transcript,
you can
Manish?
ask? Because, if you're raising the hands, I would not be able to see. Let me just stop presenting so that I can see if you're raising the hand.
Manish, you will be sending the transcript?